When we want to estimate the sign of a function, in this case our function is xyz, over a three-dimensional solid region, in this case the solid unit ball with radius up to 1, there are a few techniques we can use, but the first thing we're going to do is try to get some kind of handle on this function. If this function is greater than 0 everywhere, then the integral is certainly going to be positive. And if it's less than 0 everywhere, then the integral is going to be negative. So we're only going to have to think more carefully if this function is sometimes positive and sometimes negative. Let's begin to look at this function. How do we think about this function? I guess we would think about xyz as telling us the temperature at different points in this sphere. And so we're going to color it blue when the function is less than 0, and we're going to color it red when the function is greater than 0. And it would be really nice if the intensity of our color could tell us how much bigger than 0 it was, but that's really hard to do by hand. So when we're here in this upper octant, we have, oh, I forgot to label these. This is x, this is y, and this is z. Here in this first octant, x is positive, y is positive, and z is positive, so xyz is certainly positive. So this region is red. Down below this first octant, down in here, x is still positive, y is still positive, but z is the exact opposite of what it was before. So it's negative down here. But it's not just negative down here. These functions are perfectly matched. At this point, x, y, z, right up here, our function has some value and it's positive. At this point, x, y, z down here, these two z's are the negative of each other. Our function has the exact negative value. If I imagine drawing a little box right here and thinking about the value of this function times the volume of that box, well, the value of the function is the negative of it right here. So if I add up what's happening in those two little boxes, they add to 0. For every single little box up in this upper region, in this first octant, there's a matching box down here. And up here the function is positive, and down here the function is the exact opposite. Okay, so x, y, z, negative, which we can put in these absolute value signs because we know it's positive, negative of the absolute value of x, y, z down here. So it's the same function over the same size region, but up here it's the positive version of the function, and down here it's the negative version of the function. That means that in this 1/4 of the sphere that we're thinking about, this quarter that includes this octant up here and this octant down here, that this plus this, the function times little boxes, is going to add to 0. The net impact of this function on these two pieces completely perfectly cancels, so the contribution of those two sections to our overall integral is 0. Okay, that required us to have a pretty good understanding of this function and a good ability to visualize what it was doing in different parts. It happens that this argument works over here. It's negative up here, but positive down there, negative over here, positive down there, positive, negative, and so splitting this sphere into 4 pieces, 4 sectors, in each of those sectors the function perfectly balances and we get 0. But we're going to try a different way to reason this through as well. We imagine taking our sphere, our function was x, y, z, we want to remember that. We imagine taking our sphere and breaking it up into little first planes and then each plane into little lines. And what we want to do is figure out how the function adds up along each of these lines, and then we'll give the line a little tiny bit of width, which will create a solid, and then we can add up. what happened along this line plus what happened along this line plus this line plus this line plus this line. And once we add together what happened along all of these lines, we'll get an integral over the whole region. So here we are along this line. It's parallel to the x-axis. That's important. Whatever line we choose, we want it to be parallel to one of the axes, because then two of our variables are constant everywhere along this line, and only one of them is varying. So y is fixed along this line, and c is fixed along this line, and x is varying, and that means that the value of our function is y naught, z naught, this is a number, x. So these are both constants, and this is just some number, and that number changes. Like, so on this line, that number is different than it is on this line, but everywhere along our line, it's just the same number. So the only thing that's varying along our line is x. And on this half of our line, x is positive x times this number, and on this half of our line, x is negative times this number, and this line is going through the sphere, so it's going from, I don't know, some positive x over here to some negative x over there, and they're symmetric because the sphere is a symmetric object. So our function is 0 here, positive x times some constant, negative x times some constant. I can plot what that looks like. Positive x times some constant over here, and then negative x times some constant over here. And of course, these two sides, these two colors, so this piece of the line is red because it's positive, and this piece of the line is blue because it's negative. And the contributions of this positive part and this negative part along this single line are going to perfectly cancel. This argument didn't depend on which y naught and z naught we'd chosen for our line. So if we go to this line here, we don't know what this function, what this constant is, but we know that the x part is positive here and is negative there, and that the two sides are going to completely balance out, and that this just becomes a constant out front. And so that means that along every single little line we choose, it's going to integrate to 0, and then when we integrate over the shadow region of all of those lines that we chose, well, we're just integrating a bunch of zeros, because this point corresponds to a line that integrated to 0. This point corresponds to a line that integrated to 0. Everywhere, we just have a little line, and it's going to integrate to 0. And so that tells us that the integral of x, y, z over this very nicely symmetric w, dv, is equal to 0.